Alright, what's up everybody, year 10 specifically. I want to talk to you a little bit about graphs, distance time graphs and speed time graphs. I've had a few people ask me about this in the past couple of days, and so I thought I'd just plot a bit of information really. So a graph is just a way of representing data, and at the moment you might kind of think, oh, it's really annoying and pointless, it takes ages to plot one, and not really understand why they're useful, but they are actually really useful, especially when scientists are trying to find new relationships between data. Whoops, put a dot there, that I didn't mean to. So what you might find is you plot some points, you're given some data, and it sort of looks like this. And so you can see that there is a vague correlation. The two things seem to be going up together. I should really label my axes here so that I don't get in any trouble. So let's have time measured in seconds here, and then up here, if it'll fit, we'll have distance measured in meters. And so what I can see is that as the time is increasing, the distance also seems to be going up. Now, I could do a few things with these results. With a distance time graph, I might actually want to join the dots, which is not something we normally encourage in physics. But what you could see here is that perhaps at different points, this object was going at different speeds. Sometimes it was going fast, sometimes it was going slow, and sometimes it was barely moving at all. If we take the fastest part of the graph, that's probably going to be, looking at it, probably going to be this region here. And the reason for that is that I can calculate something called the gradient of the graph, and I can see that it's going to give me a triangle like that. Now the way you do the gradient is you kind of look at this green line here, the vertical. Let's bring it over here, and you measure how long it is on that axis. Then you do the same with this one here, but you measure it on the x-axis. Okay, so you're actually measuring the values of it depending on what you've plotted on the graph. Now finding the gradient of a distance time graph gives you the speed. In fact, I'm going to write that. Finding the gradient of a distance time graph gives you the speed. Okay, so the gradient is found, there's a few ways, like rise divided by run is one way, or delta y divided by delta x. It really depends how you've been taught it. What we don't recommend in physics is that you do the coordinate method, which is where you'll pick like a point maybe here and then a point here and do like y2 minus y1 over x2 minus x1. We don't recommend that. We recommend you draw the triangle because you do get marks for it. Okay, so I'm going to get rid of this graph for now. Now, if at any point you're not sure what's going on, rewind, watch again, and if you're still not sure, ask me on Edmodo afterwards. I want to write then, where's my pen gone? I want to write that the gradient, oh, I've already done it. The gradient of a distance time graph gives you the speed. Okay, that's good. Let's get rid of that bit then. Now let's look at the next type of graph we have. The next type of graph is a velocity time graph. So let's do some nice purple axes here. And this time I'm going to try and make my points nice and linear in one straight line. Where's the dot? That one. Let's do the points in red, and we'll have them going up something like this. Okay, so this could be some real data that you've plotted. So the first thing we do is we draw a line of best fit through the data, something like that. It doesn't have to go through the origin, but mine appears to. And this is going to be a velocity time graph, I said, didn't I? So this is going to be velocity measured in meters per second, and then over here we're still going to have the time. Now this is a different type of graph. It shows something completely different. Here what we can see is the velocity is constantly increasing. As the time is going up, the velocity is also going up. And so the object could be said to be accelerating. And in actual fact, if we find the gradient of the graph, we draw a nice triangle on it, and just like we did before, measure how big delta y is, how big delta x is, and do one divided by the other. So we do, let's actually draw it. We do a triangle delta y divided by, oh, a bit messy, delta x. And that's the gradient of the graph. Now if you think about what you're actually doing there, you're dividing velocity by time, and those of you who know your equations know that that is acceleration. So if you want to find the acceleration, you need a velocity time graph. Let's get rid of that, write some more stuff out. We'll do this in a nice purple. Finding the gradient of a velocity time graph gives you, what have I got? Email from Taz, man, teaching resources. I'm good, aren't I? Finding the gradient, that gives you the acceleration. Okay, cool. So now we've got two different graphs. We've got distance time graph, we've got velocity time graph, and we can get the acceleration, we get the speed from the gradient depending on which one we're doing. Now there's one other thing. What if I said to you, I want to know how far we travel by this time here. So like we're constantly accelerating, how far did we travel? Well, to do this, we find the area under the graph. So we draw down like this, and then we shade in, just to show what we're doing, all of this, and we find the area of it. Now, those of you who are good at math know you do half base times height for a triangle, and so if we find the area, that will give us the distance. Let's get some text there. Finding the area of a velocity time graph, I guess the area under a velocity time graph, gives you the distance traveled. Oh, can we get all that? There we go. Okay, so we've got these two here. Let's highlight that. We've got these two here for velocity time graphs, and then we've just got this one for distance time graphs, okay? If you're not sure how to do a gradient, you know, look it up on YouTube. You can find tutorials and stuff for this stuff. You should have done it in maths anyway, but like I say, make sure you draw the triangle on the graph, and you'll be good. So let's just take a look at a couple different graphs. I'm going to get rid of all of this now. So let's say we have a distance time graph first of all, and let's draw a few different things on it. So let's say, let's write this on just so we're sure, distance and time. Now, of course, I forgot my units. I'd lose some marks. You guys know what I'm doing though. So let's say we start off like this. Well, what's going on there? In fact, I'm going to change my color to a darker one, dark blue. What's going on there? Well, I'm staying at the same position, so I've got 0 speed. If I have it going up like this, then I am now moving at a constant speed. We know we can take the gradient's constant. Maybe I stop again. Maybe I go backwards a little bit, especially if this is a displacement graph and it's a vector. Maybe I go really, really fast, and then I slow down loads. And then I come to a stop again. Those are kind of all the different things that can really go on in a distance time graph, okay? Finding the area under it is meaningless. All we can do here is find the gradient. So if I wanted to find the gradient of this bit here, I'd draw a triangle, that bit, that'd be good. If I wanted to do that one, it'd be a negative velocity, but that's no big deal. I could do this one. You see, the gradient really represents the steepness. The steeper the line is, the faster the object's going. If I draw a velocity time graph over here, I'm not going to try and draw one for the same thing. That could be quite difficult. Let's label this a velocity and time. So let's kind of draw some random stuff on here. I guess we could start off like this. This would be 0 speed, 0 velocity, okay? And then suddenly we start accelerating. Our velocity is increasing, therefore we must be accelerating. Now this is the bit that always catches everybody out. What do you think that's doing? Most people would say that that is now stationary. But that is if it's a distance time graph. This ain't a distance time graph, it's velocity time graph. The velocity is constant, it's some value here. I don't know what it is, maybe it's like 20 meters per second. Depends on how you've done your scale. But it's constant, so this object is now going at constant speed. You can now have the velocity increase some more, a very steep velocity for a big acceleration, and then maybe go to constant some more. Then maybe the velocity decreases, a deceleration or a retardation. Does a little bit of constant speed, and then drops down finally with some deceleration. If you wanted to calculate the acceleration of this, all you do is the triangle. Okay, so you find the triangle here, do the gradient of this bit, that would give you the acceleration in meters per second squared. If you wanted to find the gradient of this bit here, you'd see that it's 0. That's because there is no acceleration. If you did the gradient of this bit, you get a negative number, delta y by delta x, and that would indicate that you are decelerating. I pointed out before, you're finding the gradient, you're doing delta y divided by delta x, that's change in velocity divided by change in time, that is acceleration. If you find the area underneath, maybe I want to know how far it traveled total, I'd have to add up the area of all of this. So like, I'm going to need to split it into different bits. So let's color it in first, and blah, blah, blah. And then let's get a nice, what can I use that's really going to show up? Orange. I need to find the triangle here. Then I need to find this like rectangle shape there. Then I need to find another triangle here, and then a rectangle there, and then another triangle. And then I guess I've got a rectangle and a triangle and another square and a... You know, you can see how long that would take, and you won't get one this complicated, but you could be expected to sum up the area under multiple parts of the graph. Think about it. If you're doing the area, it's like the y-axis times the x-axis. You know that displacement or distance is velocity times time from the speed equals distance over time equation. Then on this one, of course, calculate the gradient is distance divided by time, which you know to be speed, delta y divided by delta x. Anyway, that's a very quick introduction to speed time graphs and distance time graphs. I've spoken very quickly, but there's lots of stuff in your textbook about this. There's lots of stuff online. If you just Google like distance time graphs or speed time graphs, or look it up on YouTube, you will find stuff. Okay, so make sure you practice this. It will be coming in the exam, and you do need to know it. The last thing I'll show you, a very popular graph that you will get, is a terminal velocity graph. This is when an object reaches a maximum speed. Now it typically happens with a falling object, like a guy jumping out of an aeroplane. What happens is, let's draw our axes on, just because otherwise Mr. Garlic will get mad at me. Velocity and time. So what's going to happen initially, you'll almost get like a constant initial speed, but quite quickly I say a constant initial speed, a constant initial acceleration, but quite quickly the air resistance will start to build up, and what you'll eventually get, I don't know how I can pull this off, what you'll see, yeah, something like that, that's good. What you'll see is that the acceleration starts to decrease. How do I know that? Well, the gradient started to decrease, and then eventually you'll get a flat line representing a constant steady speed. So that's a terminal velocity graph. We've got three regions to it. This first region here is almost like a constant acceleration. Then we have the gradient decreasing. You can look, I can take the gradient in multiple places. Let's do it in nice green. You can see the gradient here, you know, is reasonable. Obviously you want to take more time doing this. The gradient here though is much more shallow, much less steep, and so it indicates the acceleration is less. And then of course the gradient is 0 here. So here we've got that the weight is bigger than the air resistance. Here the weight is still bigger than the air resistance, but the air resistance is steadily increasing, leading the net force to be closer to 0. And here the net force is 0. The air resistance is balanced with the weight. So if we have our skydiver here, looks something like this, he's a pretty fat guy. Then we have a down arrow like this representing his weight. And we have an up arrow representing the air resistance, which is equal. And so this stage here, the forces are balanced. There's no acceleration. Due to Newton's second law, F equals ma. I've gone into so much detail. Hopefully you understood it. And if you've got any questions, throw them on to me on Edmodo. Have a good day, everybody.